Hello and welcome to all students. In this lecture, we learn about the differential equations of first order and first degree. In the previous lecture, we defined what is meant by differential equation. After that, we defined the order of a differential equation. Now, in this lecture, we study about the elimination of arbitrary constants from the differential equation. In practice, differential equations arise in many ways, some of which we shall encounter later. There is one way of arriving a differential equation, however, that is useful in that it gives us a feeling of a kind of solution to be expected. In this section, we shall start with a relation involving arbitrary constants, and by elimination of those arbitrary constants come to the differential equation consistent with the original relation. In a sense, we start with the answer and find the problem. Method for elimination of arbitrary constant vary with the way in which the constants enter the given relation. A method that is efficient for one problem may be poor for another. One fact persists throughout because each differentiation yields a new relation. The number of derivatives that need be used is the same as the number of arbitrary constants to be eliminated. We shall in each case determine the differential equation that is of order equal to number of arbitrary constants in a given relation. So order of a differential equation and number of arbitrary constants in its solution, they are same, consistent with the relation and free from arbitrary constants. So consider one example. Eliminate the arbitrary constants c1 and c2 from the relation y is equal to c1 e raised to the power minus 2x plus c2 e raised to the power 3x. Since two constants are to be eliminated, obtain the two derivatives. So this relation 1 contains two arbitrary constants. It means that the differential equations which we get after eliminating these two arbitrary constants, the order of that differential equation must be 2, and there are two arbitrary constants, so we differentiate this relation twice. So first derivative y dash is equal to minus 2c1 e raised to the power minus 2x plus 3 times c2 e raised to the power 3x. So this is the derivative of relation 1. Again differentiate equation 2 with respect to x, and we get y double dash is equal to 4c1 e raised to the power minus 2x plus 9c2 e raised to the power 3x. The elimination of c1 from equations 2 and 3 yields y double dash plus 2 times y dash is equal to 15c2 e raised to the power 3x. The elimination of c1 from equations 1 and 2 yields y dash plus 2y is equal to, so from equation 1 and 2 we can write y dash is equal to 2y plus 5 times c2 e raised to the power 3x. Hence y double dash is equal to 2y dash plus 3 times y dash plus 2y, or finally what we have is a differential equation y double dash minus y dash minus 6y is equal to 0. Okay, so another method for eliminating the another method for obtaining the differential equation in this example proceeds as follows. We know from the theorem in elementary algebra that three equations 1, 2, and 3 considered as equation in two unknowns C1 and C2 and can have a solution only if the determinant minus y e to the power minus 2x. First column is minus y dash minus y double dash. Second column is e raised to the power minus 2x minus 2 e raised to the power minus 2x and 4 e raised to the power minus 2x. And third column is e raised to the power 3x, 3 e raised to the power 3x, 9 e raised to the power 3x. Determinant is equal to 0. So we call it is equation 4. Since e raised to the power minus 2x and e raised to the power 3x cannot be 0, equation 4 may be written with the factors minus 1, e raised to the power minus 2x and e raised to the power 3x removed as the elimination of arbitrary constants. Our determinant is like this, from which the differential equation we get is y double dash minus y dash minus 6y equal to 0 follows immediately. Okay, this latter method has the advantage of making it easy to see that the elimination of the constants c1, c2 and cn from the relation of the form y equal to c1 e to the power m1x plus c2 e to the power m2x plus dot 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 plus cn e to the power mnx will always lead to a linear differential equation like this, in which the coefficient a naught means ai's are constants. The study of such a differential equation will receive much of our attention. So consider the example number 2. Eliminate the constant a from the equation. Now here one equation is given to you. This is the relation in x and y. X minus a bracket square plus y square is equal to a square. Direct differentiation of the relation yields 2 times x minus a plus 2y dash is equal to 0, from which a is equal to x plus y dash. Therefore, using the original equation, we find that y dash square plus y square is equal to x into bracket x plus y dash square, or y square is equal to x square plus 2xy dash, which may be written in the form of x square minus y square dx plus 2xy dy equal to 0. Another method will be used in this example as an illustration of a device that is often helpful. The method is based upon the isolation of an arbitrary constant. The equation x minus a square, the equation x bracket into bracket x minus a square plus y square equal to a square may put in the form of, just simplify this bracket x square, we get x square plus y square minus 2x equal to 0, or what we have is x square plus y square upon x is equal to 2x. The differentiation of both members leads to this equation. Final equation is x square minus y square dx plus 2xy dy equal to 0. So there are many examples based on elimination of arbitrary constants. Student can take a screenshot. So example C, okay, that is also a very simple example. Example D, eliminate C from the equation cxy plus c square x plus 4 equal to 0. Okay, so there are many examples. There is one exercise. Take a screenshot and try to solve these examples. Okay, now next is a family of curve. So what is family of curve? So if we have a differential equation, then the solution of the differential equation, it gives a family of curve. Okay, family of curves of that differential equation, or the differential equation itself represent a family of curve. Okay, an equation involving a parameter as well as one or both of the coordinates of a point in a plane may represent a family of curve, or one curve corresponding to each value of the parameter. For instance, the equation x minus c square plus y minus c square equal to 2c square, or x square plus y square minus 2c x plus y equal to 0, may be interpreted as a equation of family of circles, each having its center on the line y equal to x and each passing through the origin. So figure 1 here shows several elements or members of this family. So the family of curve represented by the equation 2 is shown in the figure 1. If the constant c in equation 1 or in equation 2 is treated as an arbitrary constant and eliminated as in eliminated as in a proceeding section preceding section, the result is called the differential equation of the family represented by the equation 1. In this example, the elimination of C is easily performed by isolating C, then differentiating throughout the equation with respect to x. Thus, from x plus y raised to minus 2 divided by x plus y equal to 2c, we find that final differential equation which we get is x square plus 2xy minus y square dx minus x square minus 2xy minus y square dy equal to 0 is a differential equation of the family of circles represented by equation 1. Note that the equation 3 associates a def, uh, definite slope with each point x comma y in the plane. So plane is given here. Okay. So our job is to find a family of curve from the given differential equation, or from given differential equation or from the family of curve we can find the corresponding differential equation. So each differential equation represent a one family of curves. So there are many examples. Find the differential equation of the family of circles having their center on the y-axis. Okay, so here we have to find the differential equation of family of curves. So first of all we have to find what will be the relation in x and y, and then we find the differential equation. So the relation, the figure is given here, and the corresponding relation is x square plus y minus b square is equal to r square, and we shall eliminate both b and r and obtain the second order differential equation for the family of curve represented by the equation 10. Okay, and after differentiating this equation and eliminating arbitrary constants, we get a differential equation x into y double dash minus y dash cube minus y dash equal to 0. Okay, so here some exercise also given. In each exercise obtain the differential equation of the family of plane curve. Observe, described and sketch the several representative members of the family. Okay, so lots of problems are given here. We can try to solve these problems. Now, our main target is to study the differential equations of order 1, the differential equation of order 1, and the isocline of the equation, the isoclines of an equation. So in this chapter we shall study the several elementary method for solving first order differential equations. Before we begin that study, we shall take a brief look at some of the basic geometric ideas that are involved. Consider the equation of order 1, dy by dx is equal to f of x comma y. We can think of equation 1 as a machine that assign to each point a comma b in the domain of f some directions f some direction with slope f of a comma b. We can thus speak of the direction field of the differential equation. In a real sense, any solution of equation 1 must have a graph which at each point has the direction equation 1 requires. One way to visualize this basic idea is to draw a short mark at each point to indicate the direction associated with that point. This can be done rather systematically by first drawing curves called isoclines, that is, curve along which the direction indicated by equation 1 is fixed. Let us consider one example. Consider the equation dy by dx is equal to y. The isoclines are the straight lines f of x comma y equal to c. The isoclines are straight lines f of x comma y is equal to y equal to c. So y equal to c. For each of c, we obtain a line in which at each point the direction dictated by a differential equation is that number c. For example, at each point along the line y equal to 1, equation 2 determines a direction of slope 1. In figure 5, we have drawn several of these isoclines, indicating the direction associated with each isocline by short marker. If one starts at any point in the plane and moves along a curve whose direction is always in the direction of the direction marks, then the solution curve is obtained. Several solution curves have been drawn in figure 5. So observe this figure 5, and it gives the isoclines of the differential equation dy by dx is equal to y. Now let us consider the problem B. Use the method of isocline to sketch some of the solution curve for the equation dy by dx is equal to x square plus y square. Here the isoclines will be the circles x square plus y square equal to c, with c greater than 0, when c is equal to 1 by 4. The isocline has a radius 1 half for c is equal to 1, radius 1 for c is equal to 1, radius is 1, for c is equal to 4, radius is 2. In figure 6, we have drawn those isoclines, marking each of them with the appropriate direction indicator, and finally sketching several curves that represents solution of equation 3. So in figure 6, the isoclines and isoclines of given differential equations are given. So to find the isoclines of a given differential equation, so there are many examples given here. There is a one exercise. You can take a screenshot and try to solve these problems. Now we have an existence theorem and separation of variables. So there is one method to solve a differential equation of first order and first degree, and that method is called separation of variable. Okay, and we will see this method in the next lecture. Thank you very much.